This video goes along with section 6.5 in the textbook. The main goals are to introduce linear inequalities, talk about what those are, and then talk about graphing them, and then I'll make another video to talk about solving them. Alright, so why are they useful? In real life we have lots of situations that are not best represented with an equation. So here are two of them. I require a minimum salary of $40,000. So when you say that, if you let S equal the salary, then we're not saying something like S must equal 40,000. You would also be happy with a salary that's greater than 40,000. So we need to express that somehow, and that's why we use an inequality. So you may have seen the symbol before. If we say S is greater than or equal to 40,000, then that would allow for lots of different possible salaries as long as the minimum is 40,000. Here's another one. This is often called a compound inequality. We have two things to consider here in this second one. We need at least a dozen cups, but no more than 30. So if C represents cups, then there need to be at least a dozen of them. So greater than or equal to 12, and no more than 30. So C is less than 30. So notice in this case we definitely don't have an equation. Okay, C doesn't equal 12, it doesn't equal 30. We actually have a range of answers. So that's the main motivation for why we're taking a look at inequalities. We want to look at situations that have a range of possible answers. So here's the formal definition of a linear inequality in one variable. So eventually we'll get to ones with two variables, x and y, but we're starting out with just a single variable. And if you can write your statement in any of these four forms, ax plus by is less than 0, greater than 0, less than or equal to 0, or greater than or equal to 0, then that statement is a linear inequality in one variable. So this is just based on how we defined linear equations. Previously we said if you can write an equation as ax plus b equals 0, then that's a linear equation in one variable. Alright, so now we're really just looking at different symbols instead of an equal sign. B can be any real number, and A needs to be any real number except it cannot be 0. Okay, so if you just have, if you have A equals 0, then you would have no x, and then there's no variable, so that would not be a linear inequality in one variable. Directions you may see with these. Okay, we will work on graphing these, also solving them. So to solve means find the set of all numbers that make the inequality statement true when substituted in place of the variable. So here would be an example. Let's say 3x plus 2 is greater than 5. Okay, well one solution would be x equals 10. So if you plug in 10 for x, then we end up with a true statement. We end up with 32 is greater than 5. Okay, so x is a solution. Unlike equations, we have multiple solutions here. So another solution would be x equals 20. So when you substitute that in place of x, the statement is also true. You get 62 is greater than 5. Okay, so the solution set, now we actually do have a true set with more than one element. We want to look at the set of all such numbers, okay, 10, 20, 30, any other numbers that make this inequality true, and then we want to describe that set. Okay, so let's take a look at graphing, and we have four different examples here. So let's start with x is greater than or equal to 5. So in this section we're going to start by graphing on number lines. So we'll set that up, and the number line does continue infinitely in either direction. So usually what you want to do is focus on the thing that you're trying to graph, the number, and then just plot some of the other numbers around that one. So your number line doesn't always have to be the classic one you've seen with a 0 in the middle and positives and negatives on either side. Okay, so instead what I might do is, let's see, we'll maybe just put a 5 in the middle here. Okay, and then I'll put a few on either side. So a few numbers less than that, a few numbers greater than that. All right, so that part's sort of subjective. All right, now to show x is greater than or equal to 5, we want to graph all of the numbers that are greater than 5 or actually equal to 5. So the equal to part, you indicate that with a closed or filled circle. So you would plot that on 5. And then you would shade all of the points to the right of that, okay, because things like 6, 7, 8, and so forth, these are all greater than 5. We want to start right at 5 because this could also include things like 5.1, 5.2, and so forth. So for shading, a lot of times people will just do a different color if you had it on top of the number line. If you're using a single color, then you would just shade this really dark. Okay. Or another option, sometimes people like to go up from 5 and then over so that your arrow is very distinct. All right, so that would be x is greater than or equal to 5. Now if we move on to x is greater than 5, now we want numbers that are strictly larger than 5. So we don't want to include the number 5 itself. But we need to, we can't start at 6 because we do want to include things like 5.1, 5.2, even things like 5.00001. So we want to get as close to 5 as possible, but not actually include it. So the way to show that is to use an open circle around the 5. Oops. Okay, and then you would shade everything to the right of that. Okay, x is less than or equal to 5. So this would include the number 5 itself. So you do a closed circle, and then things that are less than 5 would be to the left of 5. And if we wanted x is less than 5, we would use an open circle on 5 and then shade everything to the right. We can also graph what are called compound inequalities or three-part inequalities. So a situation where you might use one of these is something like, I plan to spend between 400 and 600 on a tablet. So we sort of have a starting and an ending place for our range of possible answers. Now, when we say between, we've talked about this before, so between means not including. So it's kind of an odd way to say this. In real life, you might actually mean you're okay with spending 400 or 600, but mathematically, this would mean you're okay with spending, everything that's greater than 400 up to everything that's less than 600. Okay, so you would use these two symbols. Let's talk about different ways to write this. So this is one way. 400 is less than x is less than 600. This is the same thing as saying 400 is less than x and x is less than 600. So we can break these up into two different parts. You can also flip the inequalities around. So for this first one, maybe it's more natural to think of x on the left. And when you flip it, you just want to make sure that the same side of the inequality symbol faces the x. So here we want the pointed smaller end facing the 400 and the open wider end facing the x. So I would write that as x is greater than 400. And x is less than 600. All right, so that's what we're trying to graph. So I will plot a number line as before. And then here we're looking at values that are sandwiched between 400 and 600. Okay, so to give sort of a scale for this, maybe I'll go by hundreds. and maybe I'll just put a few on either side. All right. So if you graph each of these individually, if we look first at x is greater than 400, then that would mean start with an open circle on 400 and shade everything to the right. And then x is less than 600, you would start with an open circle on 600 and you would shade everything to the left of 600. But now this word and means we want to satisfy both of those conditions. So if you say that you're planning to spend between 400 and 600, that means you're not okay with spending, say, 800 or spending 200. Okay, so you only want tablets that cost in that range. So your final answer, you would look at the two graphs or the two things you've shaded, and you would look at where those two overlap. So it would be this space in the middle between the 400 and 600. So ultimately, to describe your final answer, you would end up with two open circles, and then you would just shade the numbers in between those. All right. So the first step is optional to split it up and look at two different graphs first. Sometimes that's helpful, but if you are able to jump straight from the inequality that you see to the final answer, then you would probably go ahead and do that. There's a table 6.4 in your book that gives you all of the possible solution sets for different inequalities as well as what the graphs look like. So I would probably take a look at this. One thing that you may notice from this, there are cases where we end up with an open circle on one end of a graph and a closed circle on the other. So let's say, for instance, we had 5 is less than x is less than or equal to 7. So on a number line, okay, you would want to include 7. We see that equal to part of the symbol, so that means that x could actually equal 7. But on the other side, x cannot equal 5. It's not included. All right, so I'm going to just plot a few numbers here. 4, 5, 6, 7, 8. Okay. And then we want to put an open circle on 5, a closed circle on 7, and then shade everything in the middle. So x is between those two things. All right, solution sets. We'll talk about this a bit more when we talk about solving, but your solution set would always be written in set builder notation. So you'll have these braces to indicate a set, and then you would write whatever your variable is. So in the examples we've done so far, we've been graphing things with an x. We could also use different variables like y or t or something like that. All right, so your solution would be all of the x such that, and then you just write what the final inequality is. Okay, so the one that I just did on the left, we would say the solution is all x such that 5 is less than x is less than or equal to 7. Okay, let's look at a few more graphs. So let's start with the graph of x is less than or equal to 10. All right, so I'll plot 10 and maybe a few other numbers around that. And then I want to indicate that x is, that it could be 10. All right, so I'm going to put a closed circle on 10. And then x is less than 10 would be everything to the left, so you draw an arrow to the left. If you're having trouble deciding which way to shade, what you can do is test a number on either side of the inequality. So if you want to see if you shade to the left, maybe you would test 9. So you would check, is 9 less than or equal to 10? And if so, that makes it true, so that's part of the solution. When you test 11, that makes a false inequality, so that means you should not shade to the side of the number line that has 11. All right, how about y is greater than -4? So here's -4, and I'll just do a few on either side. and then y cannot equal -4, so I'll do an open circle, and then y is greater than that, so you would shade to the right where you have the greater numbers. And then finally, let's do -30 is less than x is less than or equal to 50. So this number line, maybe I'll go by tens. So let's do -40, and then going by tens up through maybe 60. Okay, and this is subjective. Maybe you would choose to set this up a bit differently, but this sort of made sense to me. So 40, 50, and 60. All right, and then x cannot equal -30, so we're going to put an open circle there. It can equal 50, so closed circle. And then we would read this, x is between. Well, actually, we've two different symbols here, so I would probably read this, x is greater than -30 and less than or equal to 50. So we're shading everything in between those two, as well as 50 itself. All right, and that's it for graphing. So we've talked about the definition of a linear inequality, anything that can be written ax plus b with 0 and then some sort of inequality symbol between those. And then we've talked about graphing on a number line.